Students, welcome back. This is the part C of today's class, and we were looking at the conservation laws followed by nuclear reactions. So we saw a number of conservation laws which we are familiar with, like the conservation of angular momentum, linear momentum, energy, um, and then we came to number of nucleons, the nucleon number, and then we come to charge, and these things are not very difficult for us to understand, but then we have a certain conservation laws which are specific only to nuclear reactions, not other reactions. That is conservation of parity. First I talk about for conservation of spin. Now in case of spin, we know that all elements, suppose I have got a target nucleus which is like this, A, Z, and then I hit it with a particle X, and then so that I have the product particle as Y, so it will have something A dash and Z dash plus Y. So this will also have a A and a Z and A dash and Z dash. So I go on repeating that the number written on the bottom of this letter always tells us about the number of protons, and the number written on the top, it might be either left side or right side, is the number of nucleons. This is denoted by Z. We know it as the atomic number. This is denoted by A, which is equal to N plus Z, and it is known as the mass number. Now when I write this about a particle, what about a proton? Let us talk about a proton. In a proton, when I write a proton, if it is a proton, it will definitely have, a proton will have one proton, and what will be the number of proton plus neutron? Of course, it has got no neutron, so this will also be 1 like this, and this is also represented as a 1h1, which is, we know that. What about a deuteron? In a deuteron, you see, hydrogen has got 3 isotopes. Hydrogen, we know that for hydrogen we have Z is equal to 1. This is our hydrogen. That means Z is equal to 1 means what? It has got 1 proton. But then we all know that for hydrogen we have something like this. We have 3 different types of isotopes of hydrogen. In all of them we have obviously Z is equal to 1, because for a certain particular element Z is a constant. But then we have N is equal to 0, N is equal to 1, and N is equal to 2. That means these, for 1 neutron and 1 proton and no neutron, we have our well-known hydrogen, because you know that what is a hydrogen atom? Hydrogen atom has got in the nucleus only 1 proton, no neutrons. Then we have this as deuteron, which we don't use as such in our text. We don't use so much. We use it only when we go to the postgraduate level. We'll be talking about deuterons. Then we have the tritium, which is N is equal to 2. That means if I have 1 neutron added here, we get deuteron, and we have this, we get this one. So how do I write hydrogen? I write hydrogen as this, and when I talk about the nucleus, what is the nucleus? The nucleus is just 1 proton. But what about this? How do I write this one? I write this as 1 plus 1, the sum of the nucleons is 2, and like this. And what about this one? We have only one proton out here, and this is 1 plus 2, so this is equal to 3, like this. So why I'm talking about this is that because when I talk about particles, we always write it in the same format with an A on the top and a Z at the bottom. And so how do I write an electron? Electron would be like this, -1, because electron doesn't have a proton. When I talk here, and this not only tells us about the proton but the positive charge. Electron has got a negative charge, so I write here -1. And what about the number of protons plus neutrons? In electron there are neither protons nor neutrons, so this is like this. So this is how we represent an electron. And students, perhaps you are familiar with the positron. What is a positron? Positron is the antiparticle of the electron that is represented like this. So whenever you see a symbol like this, you will know that this is the positron and this is the electron. So now we know that all the components in a nuclear reaction written in this form will have a A and will have a Z value. Now that means they will tell us about the particles. Now spin. Now all elementary particles have got a spin. Suppose I hit, let me look at a common example of a nuclear reaction. Let me look at like this, 14 and 7 plus 4 He2 17O8 plus 1H1. So look at this one. In this case, how to find the parity? Sorry, the spin. We are talking about the spin. So what we do is we take like this. 14 means what? Means 7 electron plus 7 neutron. Similarly, here we have 2 proton plus, this should have been proton plus 2 neutron. That way, what about oxygen? Oxygen we have 8 protons, because 8 is written at the bottom. 8 protons plus 17 minus 8 is what? 17 minus 8 is 9, so it is 9 neutrons. That way we can count the number of nucleons out here, and we know what is the spin of a proton, a neutron, an electron. So we add up all this. So the spin out here, the sum of the spins here, but the sum of the spins here must be equal. Otherwise, the nuclear reaction would not be conserved. The spin would not be conserved, and the nuclear reaction would not be possible. That is about spin, conservation of spin. So I think I have been able to prove my point that the spin has explained to you what is conservation of spin. Now we move on to conservation of isospin. Students, we had seen in our first unit that nucleons have got a characteristic, they have got a quantum number called isospin connected with them, and isospin, all particles undergoing nuclear reactions are said to be undergoing, taking part in nuclear reaction, that is undergoing strong interactions. Nuclear reactions undergo strong interactions except radioactivity, which is a weak interaction. So in strong interactions, every particle taking place has an isospin quantum number, and that quantum number has also to be conserved in the same way as we have seen about the what do I say about the spin. So as I have seen, I have written equation in nitrogen plus alpha particles. So you see all the particles will have an isospin, so the sum will be, so if I have x plus x is equal to, not is equal to, forming y plus y, so this, the sum of the spins here plus the spin of this particle plus the sum of all the particles in this nucleus plus the spin of this, I'm talking about the isospin, I beg your pardon. So isospin will be same, will have to be conserved. This must be equal to this. And then we come finally to conservation of parity. Now in the first unit, general properties of the nucleus, we have also talked that particle has got a parity. Every particle, with every particle there is a parity, and again with the nucleus also we have a parity. So parity must also be conserved in a nuclear reaction, and actually parities of two, the sum of two particles is the product of the parity. It's like that actually. So it would be like parity if I have this and this, so it would be, I would write like this: parity is denoted by the letter pi, and pi initial would be equal to pi x multiplied by pi x, and pi final, suppose, I mean this is the initial state, so this would be like this: pi f will be equal to pi of the particle, product particle, multiplied by pi of the product nucleus, as this is the product particle and this is the product nucleus. So this is about parity, but then here we have something, we have a quantity like this, minus 1 to the power L, where L denotes the angular momentum quantum number, and this is like this. So we have this like this, we have to remember this. This is the Li, I can write it, this is the Lf, this is the final angular momentum of the initial, and this is the final angular momentum. So this is like this, this is about parity conservation. So these are the conservation laws that are to be followed for a nuclear reaction to happen. But then in case of parity there is an exception. It is seen that parity is not conserved in, which is a very interesting finding, that parity is not conserved in weak interactions. And what is weak interaction? We will know about it in the last unit of our syllabus. We'll talk about it. So parity non-conservation in weak interaction was found out, and then a lot of experiments were done, and it was found out again because people thought that how can it not be followed, because it is something that has to be followed. It is followed by all nuclear reactions. So weak interaction is a part of nuclear reaction. So it's a small part, this is small division of nuclear reaction. So this is like this, and it was later on theoretically also explained why and how this is not conserved. So I'll stop here for today, and in our next class we will be doing kinematics of nuclear reaction, where we will see what would be the Q value of a reaction, which is important from practical point of view.